Welcome to the lecture notes on statistics. Today I would like to show you classification, linear discriminant analysis, how it is working. Our data table will be the so-called iris table. This is a built-in data set, but now I separated into an Excel file. You can see here that collected data are in columns, and one separate column called species contains the type of flowers. This data set was collected by Mr. Anderson very long ago, 1970s, and he measured personally 150 flowers of three types, three varieties: Virginica, versicolor, and setosa. And with the same tool, he measured sepal length, sepal width, petal length, petal width. So sepal and petal leaves were measured, and we can use this data set to see how classification is working, whether we are able to recognize the species based on the measured geometry of the flowers, of the leaves. I will log in to RStudio, and here is the iris Excel file. I will import it first. Select the file from our class, iris. Okay, you can see here on this surface it is very comfortable. We can check how the importing is working. The name of the data set will be D as data. I recommend short name, it is very comfortable later. And we can select which sheet we want to use. We can use the default. I can see here the data. If we prepared several different sheets, we can select here. So basically it is ready to open, and we can see that yes, all data are here. Please keep in mind that if you import from text, for example, comma space delimited values, the decimal separator and the field separator should be adjusted. I have prepared already class notes for today, and you can see here that reading Excel is already done and working as I wrote already. The class notes you can download from my website. So, first, it would be nice to see what is in the data table, what we can see. And here are the data, sepal length, sepal width, petal length, petal width. The summary function gives general descriptive statistics. You can see minimum and maximum values are here. So the data range is defined this way. The mean value is the average for all. And then comes three different, more related to the distribution of the data: the median value and first and third quantile value. Basically, the median is the 50% cutting value. If we order our data from the minimum to the maximum, the middle value will be this. It means that 50% of the data is below the median value and 50% is above this value, or equal of this. And the first and third quartiles are the 25% and 75% cutting values with similar meaning. Here you can see how they are for the different measured parameters. And we have a special column, species. It is recorded, as you have seen already, for each measurement. Each line in this table, each row, is connected to one measurement, and at the end of the species we can see the name. And if we want to know what kind of names are listed, the unique function we can use, you can see here the setosa, versicolor, virginica names are inside the table. We can check it with the contingency table, and with the table function you can see that 50 pieces were measured, 50 samples we have from each variety. So it is a very well balanced experiment. If we check the correlation of the parameters, we can check what we can use to describe the flowers. You can see here that petal length and petal width are very highly correlated parameters with 0.96 above that. So maybe it can happen that we can calculate one from the other, so they could have redundant information. And also sepal length is highly correlated with petal length and petal width. The other are less correlated, but these three are higher correlation values. The default correlation calculation method is Pearson correlation. It is a linear type. So it means that these parameters are proportional to each other, or one can represent the other maybe with a small calculation. So later we can optimize our classification selecting only one of those. They are very highly correlated. It is an opportunity. We will see how it is working. First, it would be nice to see and check whether our classes could be classified at all. How the parameters, how the data look like. Because we have 4 parameters: sepal length, sepal width, petal length, petal width. I split the screen to 2 rows, 2 columns, and I prepared some plots, box plots, to see how the data looks like. And here on these charts, okay, I just want to move it a little bit away to have bigger charts. You can see that these boxes are not overlapped, so here you can see the species groups, and here are the data names what are plotted here. Sepal length, petal length, and petal width are very much separated, especially the petal length and petal width, and you can see here that the setosa looks very different from the others, but maybe versicolor and virginica could be distinguished as well using these parameters. Here I can see also some changes in sepal length parameter, but it is less obvious than here. There is some overlap maybe. Here with sepal width, I cannot see a clear difference between the different groups. Now we can check in principal component analysis whether our groups are really separated. The principal component analysis will try to calculate the so-called principal components, which are new directions based on the variability of the data. And here you can see that there is some group of data which is clearly separated from the others. According to the previous box plot, we can check here, it is very likely to be the setosa, and maybe the other two are virginica and versicolor together. And here with red arrows, we can see what is the projection of our original variables to the principal component planes when we rotate our data cloud in 4-dimensional space to find the biggest variation, how our original coordinates are projected. And here it is very important information for us that sepal width is really different from the others, and it should be used in classification, while the other 3 point to similar direction, especially petal length and petal width almost the same direction. So maybe it could be enough to use only one of them. But it is always conditional, because this is only projection of the data cloud. So it can happen that in a new dimension, these two these two vectors are really different. So let's see first how the principal components are strong. As I mentioned, the principal components are chosen according to the variability of the data. So you can see that the standard deviation along the first principal component is the highest, and then it is decreasing continuously as the next principal component we choose. And here is the proportion of variance explained by each component. The last is very weak, but altogether, when we calculate the cumulative, you can see that the 4 together can explain 100% of the variance of the data. 3 can explain 99%, 2 can explain 95% already. So maybe the first 2 can separate already one group, but probably we need all to get a complete successful classification. To do the classification, we need a package. The classification package of MDA I recommend, and here you can see the mixture and flexible discriminant analysis. This is the name of the package. I will turn it on, and to be able to use it, we can use the FDA function, which is very simple. We can describe what kind of groups we would like to recognize and with what data. We can list the parameters individually if we want to select our ones, but it is also possible to use only a dot, saying that everything else, whatever we recorded in the table, we use to try to classify the species. I go back to plots. So it seems to be possible, but now we see that whether this group is really one, and how about the others here inside. So I create a model first and then plot it. Now you can see that one group is really different from the others, and the two others have some small overlap maybe, but they seem to be here with different color, separated somehow. So the classification seems to work with linear discriminant analysis. The averages, the means of the centers of the classes are marked with 1, 2, and 3 numbers, and the different colors help to recognize them as well. The canonical variables, the x and y axis here, are similar to the principal components, what I mentioned before, so they are projections of the original data set to the classification space. And now we can check the so-called confusion matrix, how we can recognize really the classes of our samples. We can see here that the original data species, what we recorded, are here against the prediction of the model. So we had 50 pieces for each. So in lines, if we summarize, we get the 50 pieces. And in columns in this table, you can see how they were recognized by the model. The setosa was recognized very well, 100% accuracy. In versicolor, it was recognized very well. Only 2 pieces were misclassified, and only 1 piece of Virginica was misclassified. So totally we have 3 mistakes out of the total sample set. We can calculate the accuracy of this classification, since the correct classification is in the diagonal values. So if we summarize the diagonal values and see how it compares to the complete table, we can see that 98% correct classification was achieved by this linear discriminant analysis here. Okay, so we have a nice model, and it seems that we are successful teaching the computer to recognize the flowers based on the sepal and petal leaf geometry and morphology parameters. So how we can use this model later to recognize a new flower or a new sample? The first line of the table, you can see here it contains the 4 measured data and also the species information. If we compare, this is here, you can see here all the data. Yes, it is exactly, and with square brackets I refer to the first line only and all columns, so I didn't write anything here behind the comma, so I selected only the first line. And how it will be recognized? According to the prediction of the model number 2, what I created here with the Flexible Discriminant Analysis function, the first line is recognized correctly as setosa. You can check here, it was measured from setosa group and it is recognized indeed as setosa. How I can test it with any other data? Because if we have a new flower, what we would like to test, we can use this model later as a prediction model. We already teach the computer to recognize the flowers. And now I measure a new flower. First, I create a test line, like a slice from the original data table. You can see here it is the same identical line. And now I fill this line with a list of numbers. If you remember at the beginning, here are some mean values and I copied them. So it is basically something similar to the means. And a list of numbers, the last name I changed to unknown, just to make a notice to myself, so it is not something we know already, setosa vesicolor virginica. It is something I measured as a new unknown sample and would like to see which is more similar to it. It seems that it looks like versicolor. So the average of the group, which I filled the data here, it seems to be versicolor. Okay, so now you can see how to build a flexible discriminant analysis model. First, we checked how the data looks like. There were some descriptive statistics. We could have an idea what is the range of values. We checked what kind of classes we had, what is the correlation between them. With principal component analysis, we checked whether it is possible to have any to recognize any difference between the certain groups of data. And now with discriminant analysis, which is a supervised technique, we check that indeed our measured data supports this classification. So the three different varieties of these flowers could be recognized based on the geometry. And you can see here with this list of data how to test any other new measurement. The problem is that we know that 98% was the correct classification here with the original data set. This is how we could teach the system. So we are able to teach the system with this data set to recognize the flowers correctly with 98%. But if we have a new flower, which the computer never seen before, maybe the performance will be different. This we can test with the so-called cross-validation. We can validate the technique. To do that, I select randomly samples for training and for validation. So I split the original data table to two parts. The sample function will pick up random numbers from a list because there are three different varieties, setosa, versicolor, and virginica. I use them separately to have a balanced modeling. So the first part I select 10 and the second 10 and again for the third group again 10 sample. So how it is running, I make the test rows a random separation. You can see here that I have selected 30 random numbers, 15, 26, 39. If you repeat it by yourself at home, at your computer, for sure you will see different numbers. And now the original data table I split into two parts, the training and the validation. The training will have 120 rows observations and the validation 30 observations. The selection and without the selection, I split the data table. So now if I want to do the validation, I run the discriminant analysis only on the training, and using this model, I can check what is the effectiveness of the calibration. You can see here that it is almost correct because I made only one mistake with the randomly separated samples. And if I check on the validation table, you can see here that the contingency table will contain the validation section of the table and that species, and the prediction of this new model on the validation table. And now you can see here that it made two mistakes. So if we calculate the diagonal values and the ratio to the whole table, it is 93.3%. The validation is typically lower in performance than the calibration. So now you can see here that maybe the correct recognition of a new flower, which is not already in the database, in the table, could have 93.3% accuracy. Actually, this is only one trial, and maybe if you run this because of the random selection of training and validation rows in the data table, your result can be different. To be sure that it is more robust, more reliable, and not just a random value, what we can see here by chance, by our luck, we can repeat it several times. When computer programs do the cross-validation, they typically repeat it 5 or 10 times, or they calculate it as a so-called key-fold cross-validation. The key-fold cross-validation means that we have to repeat this procedure as many times as our data should play the same roles of calibration and validation to have chance to do it, and we can calculate it. We have selected 10 out of the 50. It means we have 20% validation samples. So the chance that one data can play the validation first is 0.2. And the chance that it can play validation first and calibration later, or calibration first and validation later, is 0.2 times 0.8. And if we want to know how many times we have to repeat at least this procedure to give chance any data to play both calibration and validation, it is more than 6, it's 7. So at least 7 times we should repeat this procedure to calculate an average, which already can describe more correctly what accuracy can we expect from this calibration procedure with a new, never seen before sample. So this is how the discriminant analysis is working. Now you know how to process your data set, and what we did is just use this MDA packaging, MDA package, mixture and flexible discriminant analysis, and at the beginning we checked how our data looks like. Maybe we can optimize our classification selecting the most powerful parameters, but it was not necessary now because everything was working fine. With principal component analysis, we could check that it is possible to separate at least parts of the data and how the original parameters look like, which are similar, which are not. And these were the separated classes, and here you can see also the confusion matrix, the so-called contingency table of original data and the prediction here. Now at the last step you have seen how the training and validation are working together in the cross-validation. Thank you for your attention.